Welcome back everyone to Power System, class number 16, part 2. In this class, we're going to talk about some compensation that is done in practice in the power system. We have seen that in the previous lecture, we need either capacitive compensation or inductive compensation to keep the voltage controlled. How it is done in real time, that's the goal here. So in radial power system, that means power goes only one direction right here. In radial power system, if you modify that, the same equation you have seen before, this equation you have seen before here. And if you combine them, you will see this equation here, ratio of receiving end voltage versus sending end voltage. So if you want more power, at constant voltage, so sine theta needs to go higher because you need more power at constant voltage. Sine theta needs to go higher. If delta goes higher, your cosine goes down because with higher the cosine delta value, lower the cosine value, right? To maintain the voltage, QR over here needs to be negative because this is going down here, right? So to compensate that, to make this denominator smaller, so QR needs to go negative. That means you need to supply your reactive power at the load end. That means you need a capacitor at the load end to supply the reactive power. That means you need to connect a capacitor here to supply the reactive power. That's what we have seen in the previous part. And for the compensation, if you are supplying load less than source impedance loading, your voltage needs to go up. Then you have to bring it down here with some kind of shunt reactor. If you are supplying the voltage, which is normal case, higher than your SIL, then your voltage goes down. You need some kind of capacitive support there to bring the voltage up. But here is also it's called so-called nose curve. If you have a lagging power factor, your voltage goes down drastically from what I call it, supply end to the receiving end. And if you're leading power factor, your voltage just to go up, you go towards the receiving end. And in unity power factor, you can have the almost very what do you call it? A flat profile, only loss happen to the resistive circuit, but that happen only at certain point. Look at here. So if you cross this PR by SIL ratio here, PR is the load you're supplying to the receiving end, SIL the source impedance loading at different ratio, you're gonna start collapsing the voltage curve, nose curve. So you should not exceed this ratio over here. And also a synchronous generator can supply reactive power, can consume reactive power depending on the field current, as you have seen before in chapter 3. If you have overexcited mode, you can supply reactive power. Your underexcited mode, you can receive the reactive power, so you can compensate either way. So this is only done by the field current control. So let's take a little example over here. Let's say this is the V Thevenin voltage and this is the bus voltage over here. So this is the equation for bus voltage in terms of Thevenin voltage and the line parameter over here. So let's say that your V Thevenin is as a reference, and see what happened to the bus voltage. Let's say V Thevenin over here is 120 0-degree angle, and you have your impedance over here, and also you have the current both sides. This is your leading current, this is your lagging current. With the leading current over here, let's first do the leading one. So current is leading, so your B bus would be 120 0-degree angle plus J 0.5 for the inductive reactance over there, and times J5, right? So this is the negative here. I put a positive, it's been negative, right? So then if I do the math over here, you will see that will come down to 122.5 0-degree angle, right? So that is for the leading. For leading, you can see that your bus voltage is higher than this voltage over here is acting as a source right now. So that means in leading current or you have a capacitive load, your bus voltage is higher than your supply voltage. And if you do the bus voltage for the lagging power factor over here is 120 0-degree, negative 0.J5, then negative J5, and if you do the math over here, that will come down to 117.5 0-degree. That means now your bus voltage is lower than your Thevenin voltage of the source, that means in lagging, your bus voltage is lower than your supply voltage. So that the thing here. So by leading and lagging power factor core impact the bus voltage. What is done in the practical field? For this one here, you have thyristor here. Thyristor can be turned on and off by using a signal at a particular delay time. That is called alpha, delay angle over here. So that delay angle will get the amount of compensation you need for this particular case. So this is the capacitor. You're ignoring this one. This one is there just to minimize the transient. And how much your capacity reactance you're getting depends on your alpha when you're turning on and off these two thyristor, and that what is the leading current over here. So this is the bus voltage is the leading over here, right? So that will support the voltage up when you need them by supplying capacity reactive power, and it depends on the what do you call it, alpha of the firing angle. Same thing could be done for thyristor control reactor, whose inductance. Again, that how much inductive reactive power you need, that depends on, again, firing angle. So that is the lagging current over here. So if you put them together, you can support the both sides. This is the inductive side, this is the capacitive side over here. So your voltage this time, this side will, when time to voltage goes up, this side will bring the voltage down. When time to voltage goes down, this side will bring the voltage up. So you have a balance on both sides by firing these thyristor as you need them through a computer program. And also you can do the series thyristor control series capacitor. That means your capacitor is right here. Again, you're controlling them using this thyristor. So how much capacitance you need overall in the line to compensate the series inductance, you can also depend on the firing angle. So recap here, we did transmission line modeling, we did the transmission loading and source impedance loading, transmission line compensation, we discussed the compensation of transmission lines, and also we discussed how it has been done in the practical field. It's called flexible AC transmission system, FACTS, and we will answer your question in the class, as well as we'll do some example in the class. That's all, everyone. So I'll see you in next class.